Welcome my dear learners for this course on mechanical vibrations. In this module 2 we are discussing on forced vibration and vibration measuring instruments. So far we have solved 9 numerical problems on forced vibration. Let us continue from the point where we have stopped in our previous lecture. In today's lecture I am heading to solve problems on forced transmissibility. The problem number 10 of our discussion on forced vibration states that a machine of mass 1 ton is acted upon by an external force of 2450 newtons at a frequency of 1500 rpm. To reduce the effects of vibration, isolators of rubber having a static deflection of 2 mm under the machine load and an estimated damping of 0.2 are used. Determine the force transmitted to the foundation, the amplitude of vibration of machine, the phase difference between the amplitude of vibration and the excitation force, and the phase lag between the force transmitted and the excitation force. Let us solve this problem. If we list out the data given for problem number 10 of our discussion on forced vibration, we have a machine of mass 1 ton. Mass of the machine is given, which is 1 ton. 1 ton is nothing but 1000 kgs. Is acted upon by an external force. Magnitude is F0, which is 2450 newtons at a frequency of 1500 rpm. So as given excitation speed N, which is 1500 rpm. To reduce the effects of vibration, isolators of rubber having a static deflection delta, static, which is 2 millimeters under the machine load are estimated with the damping factor zeta of 0.2. Let me convert this static deflection to meters. It will become 2 into 10 to the power of -3 meters. Determine the force transmitted. So he is asking us to calculate Ft, amplitude of vibration A, the phase difference phi, and the phase lag between transmitted force and excitation force, that is phi minus alpha. Now let us solve this problem. If I move ahead for solution of our problem number 10, we know mass, we know deflection. So using deflection, whenever we have static deflection, we know that natural frequency is given by root of g by delta, right? And we have excitation rpm, speed 1500 rpm. So therefore excitation frequency will be 2 pi n by 60. So recollecting the basics, if I move ahead, we have the natural frequency omega n, which is given by root of g by delta static, where g is acceleration due to gravity, which is given by 9.81 meter per second square, and static deflection is turning out to be 2 into 10 to the power of -3 meters. Hence the natural frequency for the problem will become root of 9.81 meter per second square divided by 2 into 10 to the power of -3 static deflection. Hence the natural frequency for this problem is 70.036 radians per second. Now we have excitation speed. Using that I can find excitation frequency omega, which is given by 2 pi n by 60, where n is in rpm. So if I substitute and solve, I will get 2 into pi into 1500 divided by 60, which is nothing but 157.08 radians per second. 157.08 radians per second. We know omega n, we know omega. Now let us move for the first unknown, that is force transmitted. Recollecting the transmissibility ratio. The formula for transmissibility ratio is already known for us. If I recollect the formula, we have Ft by F is equal to root of 1 plus 2 zeta omega by omega n whole square divided by root of 1 minus omega by omega n whole square 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square under the root. Correct? Now let me determine the frequency ratio omega by omega n. So if I calculate the frequency ratio omega by omega n, we'll get the answer as 157.08 divided by 70.036. The frequency ratio for the given problem is 2.423, which is dimensionless. 2.423. Now substituting the values which we have, I can determine what is the force transmitted to the foundation. The force transmitted to the foundation is equal to excitation force times this value, right? How much is the excitation force? 2450 newtons. 2450 newtons is the excitation force times we have root of 1 plus 2 zeta. Omega by omega n is 2.423, whereas zeta is 0.2. Let me substitute the values and solve directly. So we have 2 zeta, 2 times 0.2 is the damping factor, and the frequency ratio is 2.423. 2.423 whole divided by root of 1 minus 2.423 square whole square, plus again we have 2 zeta, the damping factor is 0.2 and frequency ratio is 2.423 whole square under the root. Now if I solve for force transmitted to the foundation, we have excitation force as 2450 newtons times 1 plus 2 zeta omega by omega n whole square, which is 2 into 0.2 into 2.423 whole square divided by square root of 1 minus omega by omega n square, that is 2.423 square whole square, plus again we have 2 zeta, 2 into 0.2 into omega by omega n is 2.423 square. So if I solve, I'll get the transmitted force as, the force transmitted to the foundation is turning out to be 687 newtons. The force transmitted to the foundation is 687 newtons. Now moving ahead for amplitude of vibration. Now to find amplitude of vibration, we don't know amplitude of excitation, but we know force. Force is known for us, so hence I can use the general equation for amplitude ratio, that is magnification factor. So recollecting the magnification factor, I can find what is the amplitude of vibration. So recall magnification factor, because magnification factor is a general expression using which we have derived expressions for reciprocating and rotating unbalance, support motion, as well as force transmissibility. So therefore recollect the basic formula what we have derived, that is magnification factor, which is given by A divided by XS. XS is static deflection, which is equal to 1 divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, right? Now what is the value of XS? The formula for XS is also known for us. XS is F naught by K. XS is F naught by K, right? Now how much is K? Stiffness. Stiffness is not given here, so stiffness is nothing but stiffness K is equal to mg by delta S. Make a note of it. Stiffness is given by the formula force per deflection. How much is the force? If you carefully observe the problem, he states that the damping provided deflects 2 mm under static load, under its own weight. How much is the own weight? mg. M is how much? 1000 kg. So if I substitute, I will get K value as M is 1000, correct? M is 1000 into G is 9.81 divided by delta is 2 into 10 to the power of minus 3. Hence the stiffness K will become 1000 kg into 9.81 divided by 2 into 10 to the power of minus 3. So stiffness is 49 lakhs 5000 Newton per meter. Now use this stiffness, we know excitation force F0, hence I can find the excess. Excess will become what? F0 is 2450 divided by stiffness is 490,500. Hence I will get excess will be 2450 divided by 49 lakhs 5000 Newton per meter is the stiffness. So excess is turning out to be 5 into 10 to the power of minus 4. 5 into 10 to the power of minus 4 meters. Now if I substitute and solve, I will get the amplitude of vibration. Amplitude of vibration for this problem will become A is equal to 5 into 10 to the power of minus 4 divided by square root of, what I get, 1 minus omega by omega n is already known, 2.423 square whole square plus 2 into zeta is 0.2 into 0.243 square under the root, right? Hence amplitude of vibration will become 5 into 10 to the power of minus 4 divided by square root of 1 minus omega by omega n square, that is 2.423 square whole square plus 2 zeta is 0.2 into omega by omega n is 0.243 whole square. So amplitude of vibration is 1.024 or 1.025 into 10 to the power of minus 4 meters, which is nothing but 0.1025 millimeters. 0.1025 millimeters. Next, we have calculated what is the force transmitted. We have calculated what is the amplitude of vibration. Next, he is asking what is the phase difference between the amplitude of vibration and excitation force. That is, third one, he is asking phi. We know that tan phi is given by 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So hence phi is equal to how much? Tan inverse of 2 into 0.2 into 2.423 divided by 1 minus 2.423 square. Hence phi will become shift tan inverse of 2 into 0.2 into 2.423 divided by 1 minus 2.423 square. So phi is turning out to be minus 11.2535 degrees, or we already know that tan 180 plus theta is tan theta. So therefore I can add 180 for this. This plus 180 is nothing but 168.746 degrees. So the answer is 168.746 degrees. Now he is also asking us to find the phase lag between the transmitted force and the excitation force, which is phi minus alpha. Hence I should calculate alpha first. So let me calculate alpha first. We know that tan alpha is given by the equation 2 zeta omega by omega n. Hence alpha will become how much? Tan inverse of 2 into 0.2 into omega by omega n is 2.423. Hence alpha for this problem. Hence the phase lag phi minus alpha, that is phi minus alpha is nothing but force, the angle between the force transmitted to the base and the excitation force, the angle between these two. The angle between these two is phi minus alpha, which is turning out to be phi is 168.746 minus alpha is 44.104. Hence the phase lag will become 124.642 degrees. So this is the solution for problem number 10, where in which we have calculated what is the force transmitted to the foundation and amplitude of vibration, and also phase difference between the amplitude of vibration and excitation force, and phase difference between the force transmitted to the foundation and excitation force for vibration. Let me pause this video for a while so that you people can copy it down. Later we will solve problem number 11. Before moving ahead for problem number 11, one careful observation is that here excess should be calculated with using the formula F naught by K, which we have already derived in the lecture 1 of this module, where F naught is nothing but excitation force, where K is the stiffness. So stiffness, general equation for stiffness is force per deflection. We know static deflection. Static deflection is 2 millimeters. How much is the force? This deflection is based on the self weight. Self weight is 1 ton, right? So therefore it is 1000 kg into 9.81 by static deflection. So if I substitute and solve, I will get the value of stiffness. Now use excess is equal to F naught by K. You will get excess as 5 into 10 to the power of minus 4 meters. Make a note of this. This formula holds good for all the types of formulas what we have, all the types of problems what we encounter in forced vibration analysis, because this is a general formula using which we are calculating the amplitude ratio for various cases. Hence we can use this formula for all the cases of problems what we discussed in forced vibration analysis. Let me pause this video for a while. Next, moving ahead for problem number 11, which states that an air compressor of 450 kg operates at a constant speed of 1750 rpm. Rotating parts are well balanced. The reciprocating part is 10 kg and the crank radius is 100 mm. The mounting introduces a viscous damping of damping factor 0.15. Specify the spring for the mounting such that only 20% of the unbalanced force is transmitted to the foundation. Find out the amplitude of transmitted force. If I list out the data given, what we have for problem number 11, that is an air compressor of 450 kg. Mass of the compressor is given, which is 450 kg, operates at a constant speed. The operating speed of the compressor is 1750 revolutions per minute. Rotating parts are well balanced. The reciprocating parts of 10 kg at a crank radius of 100 mm is creating the unbalance. So how much is the reciprocating masses part? M naught is 10 kg and crank radius is nothing but eccentricity, which we have already discussed, that is 100 millimeters, which is nothing but 0.1 meter. The mounting introduces a viscous damping of damping factor zeta 0.15. Specify the spring means what? Specify the stiffness of the spring. If only 20% of unbalanced force is transmitted, that is transmission ratio Ft by F is 0.2, and also find out the amplitude of force transmitted, that is F naught. Ft by F naught is 0.2. Find out F naught also is the question he is asking us. Right. Let us solve the problem. If I move for solution, we have, since the transmission ratio is specified for us, let us use the equation of transmission ratio. We know that transmission ratio is given by root of 1 plus 2 zeta omega by omega n whole square divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square under the root. Correct? Now we know transmission ratio, we know the value of zeta, but we don't know what is the frequency ratio. Let me calculate frequency ratio from this formula by substitution. We have transmission ratio as 0.2. 0.2 is the Ft by F transmission ratio. Squaring on both sides, I will get 0.2 square is equal to 1 plus 2 into zeta is how much? 0.15 into omega by omega n whole square divided by 1 minus, I don't know what is the value of omega by omega n whole square plus 2 into 0.15 into omega by omega n whole square. Now we know all the values except frequency ratio. Now if you carefully observe, this equation is of the order 4. Right? This equation is of the order 4. So it is a fourth order equation. Hence let me solve this properly, for which let me take the frequency ratio omega by omega n as R. If I take omega by omega n as R, I will get 0.2 square is 0.04 is equal to 1 plus 2 into 0.15 square is 0.09 R square divided by 1 minus R square whole square plus, this is already known, right? It is 0.09 R square. Correct? Now this is of the form a minus b whole square. A minus b whole square can be written as a square plus b square minus 2ab plus 0.09 R square. This is equal to, divide, I have interchanged the positions, cross multiplied. So I will get 1 divided by 0.04 which is 25 plus 1 divided by 0.09 which is 2.25 R square. Now simplifying further, I will get R to the power of 4. Here I will get minus 2 R square, that is minus 2 plus 0.09 R square plus 0.09, and if I take this to LHS, it will become minus 2.25 R square. So simplifying which, I will get minus 4.16 R square minus 24 is equal to 0. So this is the equation what I will get. Now decomposing it further, let us take further y is equal to R square, because to convert this into quadratic equation. So the quadratic form of this equation will become y square minus 4.16y minus 24 is equal to 0. Now I can find the roots, that is using equation of degree 2, we have 1 minus 4.16 minus 24. So I'll get the value of y1 as 7.402 and y2 as minus 3.24. Now we know that y is equal to r square, so substitute for y, we will get r square is equal to, that is r1 square is equal to 7.402 and r2 square is equal to minus 3.24. So this is imaginary, leave it, because root of minus is imaginary. Now take this one. So if I take this, I will get r1 as root of 7.402. Root of 7.402 is nothing but 2.72. This is valid, whereas here I will get imaginary root, that is invalid. So hence I can adopt r as 2.72. So we got the value of r. Now use it. R is equal to omega by omega n. So therefore omega by omega n is 2.72. How much is omega? RPM is known, hence I can find the value of omega. Omega is 2 pi n by 60. N is 1750, hence omega is 2 into pi into 1750 by 60, which is nothing but 183.26. 183.26 radians per second. Now I can find the value of natural frequency omega n, which is omega by 2.72, that is 183.26 by 2.72, which is nothing but 67.375 radians per second. Clear? I found out omega. Substitute omega here, divided by 2.72, will get the value of omega n. So I found out omega n. Now I can find what is the stiffness. So we know that omega n is equal to root of k by m, hence k is equal to omega n square into mass, hence stiffness will become 67.375 square into how much is mass? Mass is 450 kg, hence you will get the stiffness as 67.375 square into 450, which is nothing but K is equal to 2042726 newtons per meter. We got the value of stiffness, that is 20,42,726 newton per meter is the stiffness. Now I want to find the force transmitted, for which the force, excitation force, is also unknown. If you carefully observe the problem, this is the problem on reciprocating unbalance. For reciprocating unbalance, whatever we have already discussed for rotating unbalance holds good. So therefore the excitation force for reciprocating unbalance is nothing but the excitation force equation what we use for rotating unbalance. Hence the excitation force, will be how much? That is F naught is equal to what? M omega square r. R is nothing but radius. Don't get confused with this one. This is frequency ratio. Let me, to avoid confusion, let me put it as r dash, so that we'll avoid confusion. R dash square, R dash. R dash stands for frequency ratio, whereas R stands for radius. Don't get confused. This is for frequency ratio, this is radius, this is not frequency ratio. M omega square R, centrifugal force. Therefore, how much is F naught? F naught is M into excitation frequency is 183.26 square into radius of rotation, radius of crank, that is eccentricity, is known. M omega square R is nothing but M omega square E. How much is E? 0.1 meters. Clear? Hence F naught will be, here the excitation force is created by M naught, not by the overall mass, correct? M is the total mass including the unbalanced mass, whereas M naught is only unbalanced mass. So unbalanced mass is how much? 10 kg. So substituting 10 kg as the unbalanced mass, what he has given, which is rotating at a radius of 0.1 meters, we'll get the answer as 10 into 183.26 square into 0.1. So F naught is turning out to be 33,584.23 newtons. We know transmissibility ratio, hence force transmitted will become how much? Ft by F is 0.2, hence Ft, force transmitted is 20% of this into 0.2, which is 6,716.846 newtons. So this is the magnitude of force transmitted to the foundation. So this is the solution for problem number 11. Let me pause this video for a while so that you people can copy it down. Later we'll discuss problem number 12. Now moving ahead for problem number 12, the weight of an electric motor is 125 newtons and it runs at 1500 rpm. The armature weighs 35 newton and its center of gravity lies 0.05 centimeter from the axis of rotation. The motor is mounted on 5 springs of negligible damping so that the force transmitted is 1/11th of the impressed force. Assume that the weight of motor is equally distributed among the 5 springs. Determine stiffness of each spring, dynamic force transmitted to the base at operating speed, natural frequency of the system. If I list out the data given for me in problem number 12, if I list out the data, we have the weight of electric motor. The weight of electric motor is 125 newtons and it runs at 1500 rpm. RPM is 1500. The armature weighs 35 newton. So weight of armature is given, which is 35 newtons, and its center of gravity lies 0.05 centimeter from the axis of rotation. What do you mean by this distance between center of gravity and axis of rotation? Yes, you are correct. It is eccentricity E, which is 0.05 centimeters. The motor is mounted on 5 springs of negligible damping. So he has given number of springs as 5, so that the force transmitted, that is the transmissibility ratio, that is Ft by F naught is 1/11th of the impressed force. Assume that the weight of the motor is equally distributed among the 5 springs. Determine stiffness of each spring. Stiffness of each spring, dynamic force transmitted, and natural frequency of the system, omega n. Let me solve this problem. If I move for solution, he has given the weight of electric motor. So weight of electric motor, this is of motor, correct? Hence mass of motor is how much? 125 by 9.81, which is 12.74 kg. He has given the speed, and this is required conversion. Mass of armature Mass of armature is how much? 35 by 9.81, that is 3.5677 kg. 3.5677 kg. Now eccentricity is specified. E will be 0.05 into 10 to the power of minus 2 meters. Now if I carefully analyze the data given, what we have, we will get n is 1500 rpm. Now the total mass of the system must be the entire mass of the system, that is mass of the motor plus mass of the armature together should give us the total mass. So therefore total mass is how much? Total mass is m, which is 12.74 plus 3.564. 12.74 plus 3.5677, because the mass m should be including the eccentric mass. Here he has given the motor mass separate and the eccentric mass separate, so therefore total mass must be sum of these two, which is nothing but 16.3 kg. 16.3 kg. How much is eccentric mass? m naught, it is 3.57 kg. So it will become 31. What else? Eccentricity is given. E is 5 into 10 to the power of minus 4 meters. 5 into 10 to the power of minus 4 meters is the eccentricity given. Correct? So let us take this as the data and solve. I simplified the given data into the data which can be easily readable and adaptable for the expressions what we have derived so far. So use this as the data and solve. It will give us a simplified solution. Next, if I move for solution of this problem, he has given the transmissibility ratio, correct? Hence I will use the equation of transmissibility ratio. We know that transmissibility ratio, that is force transmitted to the excitation force, is given by square root of 1 plus 2 zeta omega by omega n whole square divided by root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square under the root. Correct? Now he is stating that the springs have negligible damping. So damping is neglected. Negligible damping given in the question. What does negligible damping means? Zeta is 0, right? So therefore I can take zeta as 0. Damping is negligible. So if I take zeta as 0, what is the equation for transmissibility ratio I am going to get? I will get the transmissibility ratio equation as 1 divided by 1 minus omega by omega n whole square. Whenever you encounter the equation in this form, I have given a very important note. What is that note? Whenever we have equation in this form, always we should verify whether the equation satisfies the condition to move further. That is, if LHS is unknown for me, I know only RHS. In such cases, I should verify whether omega by omega n is greater than 1 or less than 1. If omega by omega n is greater than 1, then the RHS will become negative. So therefore, to avoid that, I should interchange the term. That is one thing. Second thing, if I know LHS, I don't know RHS. In such cases, the LHS must be always greater than 1 for this case. Otherwise, you should interchange these two. This is because of the reason, otherwise you are going to get the imaginary answer. You are going to get the imaginary answer. What I mean to say is that whenever RHS is unknown, verify LHS. LHS should be greater than 1. If not, interchange the denominator of RHS. That is, in the LHS, the denominator must be greater than numerator, or the ratio of LHS must be greater than unity. That is, I already given that note. Let me give that note once again. note that if omega by omega n is greater than 1, or the ratio if TR is less than 1, this is always the case, correct? This is always the case. Transmissibility ratio is always less than 1 for undamped system. This is only for undamped system. Always take, if any one among these two prevails, you always take transmissibility ratio as 1 divided by omega n whole square minus 1. Take it in this form. Kindly make a note. Now I can move further. So since this is holds good here, because TR is 1 by 11, which is less than 1, I should use this form. So therefore transmissibility ratio should be taken as 1 divided by omega n whole square minus 1. This is because otherwise if I use this, I will get the answer as imaginary. Now moving further, transmissibility ratio is known 1 by 11. So substitute and cross multiply, I will get omega n whole square minus 1 as 11. What I have done, I substitute transmissibility ratio as 1 by 11 and cross multiplied. So this will come to numerator, 11 will go here. Now how much is omega by omega n? Omega by omega n is root of 12, which is nothing but square root of 12 is 3.464. 3.464. Now we know RPM, I can find omega. So omega is 2 pi n by 60. N is 1500. Hence it is 2 into pi into 1500 divided by 60, which is nothing but 157.08 radians per second. Now I can find the natural frequency. Omega n is equal to omega by 3.464. This divided by 3.464, which is 45.346 radians per second. In terms of hertz, this must be divided by 2 pi. So in terms of hertz, it is 7.217 hertz. So Fn is omega n by 2 pi, which is nothing but 7.217 hertz. Done. I calculate the natural frequency. Now I can find what is the spring stiffness. If I move for spring stiffness, we know that omega n is equal to root of k by m. Hence k is equal to omega n square into m. So therefore k will become 45.346 square. 45.346 square into total mass. Total mass is 16.31 kg. Hence the total stiffness will be 45.346 square into 16.31. That is 33,537.6 Newton per meter is a total stiffness. But we have how many springs? 5 springs. So stiffness of each spring will become what? Stiffness of each spring will be equal to K by number of springs. K by number of springs, that is 33,537.6 by 5. So stiffness of each spring will be 6,707.5. 707.52 Newton per meter is the stiffness of each spring. Now we have done the stiffness of each spring. Moving ahead, I want to find force transmitted. To determine the force transmitted, first I should determine what is the excitation force. The formula for excitation force is known for us. That is, the formula for excitation force is already known for us. F naught will be m naught omega square E. This we have already learned through our discussion on rotating and reciprocating unbalance. We know all the values. If I substitute and solve, the excitation force will become how much? Eccentric mass is 3.57 into omega. Omega is 157.08 square into eccentricity is 0.05 into 10 to the power of minus 2 meters. Into 10 to the power of minus 2 meters. So if I solve, I'll get the excitation force as 3.57 into 157.08 square into 0.05 into 10 to the power of minus 2. The excitation force is 44.04 newtons. Hence, force transmitted to the foundation. Hence, the force transmitted to the foundation will be Ft, which is equal to transmissibility ratio into F naught. Hence, force transmitted is, transmissibility ratio is 1 by 11. 1 by 11 into 44.04 is 4 newtons. So this is the complete solution for problem number 12. So in this lecture, we have addressed problems on transmissibility of forces. In our next lecture, I will take up numerical problems on critical speed of shaft. That's all from this lecture. Thank you all.